What's up, YouTube? So today I just wanted to talk briefly about graph algorithms because they are very much on my mind after adding pathfinding to my dinky tower defense game. So let's get into it. So generally, graph algorithms refer to any algorithms that do something with graphs, which are which are collections of nodes and edges. And these nodes could be anything like world states. They could be physical locations, which is typically how they are used in like in like games and stuff. And then the edges will connect nodes together in whatever certain ways. So physical locations is a pretty intuitive application of graphs. If you look at any map, then there's a whole host of different ways it can be broken down into a graph structure. You could have like nodes that are zip codes. You could have intersections of like street maps. You could have cities, you could have school districts, whatever. And then the edges are then just a relationship of some kind of adjacency. World states is a bit more unintuitive, but if you think of something like a chessboard where each configuration is a node and then the edges that move toward that node are all the single moves that result in that configuration, and then the edges away from it are all of the single moves that can occur out of that configuration. Maybe that helps. Just a quick fun fact: I don't know how modern chess AI works at all, really, but a graph traversal plus evaluation method is more or less what the minimax algorithm is, where you would basically pick moves that result in the best evaluation for your position and the worst evaluation for your opponent's position. And then also just like another example of what the like how a world state could be put into a graph node. In school, for my intro to AI class, our pathfinding project was to solve the flashlight problem, which is where you have where you have a number of people. You have like A, B, C, D, or whatever, and then there's a bridge, and then they have to get to the other side. There's a single flashlight. Only two people can cross at any time, and each person moves at a different speed, and so you have to take over pairs of people. So like, you would have to take over C and D, and then they would go over here, and then someone has to bring back the flashlight, and then each node was then a state of something like the list of people on each side, where the flashlight was, and then the cost to get to the current state, and then the cost would be like, how long it's taken to get to this current point. So with all of that, there are a lot of problems that graph algorithms can solve, but the ones most commonly discussed are things like searches. I'm really bad at using this this software. Sorry. This is Krita, by the way. Is there a way I can just like new thing? Yeah, cool. No. Okay. So can you stop zooming? Whatever. So the ones most commonly discussed are types of searches, which is where you're trying to find like a certain node that has a certain condition, typically from like a starting point. This would be things like you're trying to find a chess position where you have checkmate, or you're trying to find I don't know, like an intersection that has like some kind of criteria. Then there's also routing, where you're trying to find a path fulfilling some criteria, such as like travel to each node exactly once and then return to the origin. We have like a big list of cities and something, and then you try to find a way to get to each one, return to the origin, and then like find the shortest path, find the shortest path that does that. That is also known as the traveling salesman problem, which is it's a whole can of worms. Then there's also things like find the shortest route to a certain node. So this is common in like pathfinding, where if you have like some kind of like wall or like a river or whatever, and you're trying to get a unit from here, from here to here, then like what's the best way to do it? Is it to go this way? Is it to go this way? What if there are like mountains here? Pathfinding. And then there's also things like sorting, which is used in dependency manager version resolution or task scheduling algorithms. For example, like if you have, a list of tasks like, A, B, C, and, C relies on, or C must be done after A, B must be done after C or whatever, then graphing, representing this as a graph and then doing some topological sorting is one way that you could solve this problem. As you can see from Wikipedia, though, I will put Wikipedia here. There are a lot of other problems that can be solved with them. And so depending on the problem, the components of the graph can have different characteristics. So I mentioned that a node can basically contain any kind of data, like chess configurations or states of the flashlight problem, but the edges themselves can also have some kind of data. So for example, in a directed graph, edges will only go one way. So if this was a directed graph and this was an edge that went from A to B, then this means that there's no way to go from B to A. We would have to either have some other path through directed edges that eventually lead to A, or we would have to add another edge from B to A or something like that. In an undirected graph, an edge just connects two nodes. So A and B are just connected. You can go from A to B, you can go from B to A. The other common piece of data that I've seen is cost or distance or length or something like that. This is important in things like pathfinding. So for example, in games like Civilization, if you are over here and then there's a bunch of mountains, and then over here is Gandhi, and you are trying to rush him before he gets nukes, it's going to take longer because of all of the mountains on the way there. So that's in pathfinding, that's another thing that you have to consider. And so as far as I know, pretty much any graph algorithm requires some form of traversal. Then that has two basic shapes, and then everything is kind of a generalization on top of that, or is a specification on top of that. So the two kinds of ways are, let's just make like a really simple graph, right, or grid. And so if we, for example, start here, then and then we want to we just want to traverse the grid and find whatever, find the distance to each node from the starting point. Then we can either go outwards, we can either travel every single node, or how to explain. Before we get into that, actually, before showing the difference, let's look at what it means to traverse a graph at a basic level. So we need a starting point, so we'll do this again. Sometimes, like in pathfinding, this is a known node, or in dependency resolution, it's your application, and then the connections would be all of your application's explicit dependencies. Sometimes you can just pick a node, like if you're doing graph coloring, then it doesn't really matter where you start. But in any case, you need a starting point. And then that goes onto a list of nodes that is like your explore list. So we'll denote this by, let's see, this is 2, right? So we have 2 is the list of nodes that we're going to look at. I'm going to zoom out on this a little bit so that it shows up more in the stream, or in the thing. And then let's see. Yeah, so then from here, if you're doing pathfinding, then this is where you would set its cost to get to it to 0. If this was like a topological sort, then you would put its placement in the topology as the only placement so far. Whatever, it gets like the default treatment, right? From there, you also add this node to a visited list once you've done all of the things with it. Which I guess actually I should have written the script better. What we need to do now is then we need to expand the explore list, and so we're going to add all of the adjacent nodes. So not 0, we'll do 1, 1, 1, 1. We'll just assume that every traversal is just every edge is just a 1 cost edge. So then you would also add what is this, to 1? You would add what is that? 1, 2. You would add 2, 3, and then you would add 3, 2. Basically, x plus 1 and x minus 1, and then x plus 1 and or y plus 1 and y minus 1, and then like every combination of that. Or if you're only doing like north, up, down, left, right as your traversal directions, then it would just be the subset of that, where it's you do one or the other. And then you put the current node on a list of visited nodes. And then where is eraser? Where is eraser? Where is eraser? There you are. Okay. And then we remove it from the explore list. Wow. Good enough. And then we are done with this node. And then depending on the type of traversal, we then pick a node from the explore list. So, maybe we do 2, 1, maybe we do 3, 2. Doesn't really matter. We just pick a node. Or it depends on the type of traversal, rather. And then we make this our new traversal point. So if we were doing 2, 1, so then that would be this guy is now our this is where we're starting from. So we assign its cost to as 1 because that was the edge. That was the current cost to get to this node based on the edge, right? And then we take all of its adjacent nodes. We take all of its adjacent nodes. So we take like this one, we take this one, we take this one. We do not take this one because it already exists in the visited list. But we take these other 3 nodes and then we put them onto our explore list. So this would be what is that? 2, 2, 0, 1, 1, and then 3, 3, 1, right? And then we basically just do this. We go to these, and then we give them the cost of 2. We would eventually go over here and do the same for these, and then these would get 3. These would get 4, 5, 4, etc., etc. Right, and that's pretty much what the traversal looks like. And one thing to note is that one like kind of implement, or one way that you can make checking the or adding nodes to the explore list faster, since you need to check that it doesn't exist in explore and the visited lists, you can also represent these as sets. If your language supports that. C doesn't really have like a built-in set, so if you would have to like build it yourself. I don't know what that looks like actually. So, but I think Zig has a set in the standard library, but C++ has one, and it's in the STL for sure. But anyway, you can use sets for these lists as well. Also, since you don't need to care about like the positioning of things in the general case. So then it depends. Right. So then there are types of traversal, right? So there's breadth first search and depth first search. And basically the difference is how can I just like wipe the whole thing? That's not what I want. Okay, we'll just make a new thing. Close that. So basically, so for breadth first search, BFS, also called BFS, you add things to the list to the end of the list. So like you have your list, and you put nodes on we'll say like 1A is just one of the nodes starting from node 1. Is one of the nodes connected to node 1. And then 1B, 1C. And then you would do something with 1A, and then all of those nodes then go on to the end. So you would then be left with 1B, 1C, 1AA, 1AB, or whatever. and then you always take from the front. So this is also known as a queue. This is also the data structure called a queue, which is also called a first in, first out data structure, because the first items that you put in are the first ones that you take out. Then the I don't know what I did. Whatever. So then the other kind of, I guess I could have just like moved the thing. So then the other kind of basic shape is depth first search, which is where you basically do kind of the inverse, right? So like when you add the nodes from node 1 to your explore list, you would actually add the way that it would look is you would go from 1A is your explore list to, you would then add 1B in front, and then 1A becomes the last thing and stays in last. And then you would next add 1C to the front, and then you would at the end of it you would have this as your explore list. And then you would just take again from the front of the list, and this is called this is also known as a stack data structure. This is distinct from the like location in memory, where functions and things that are like things that are like statically allocated hang out. That different from that stack. This is just a like how you put. This is just how a way that you can like put things on and take stuff off of a data structure. It's very familiar to players of Magic the Gathering. Whenever you respond to spells and stuff with abilities, those go onto the stack, and then those resolve in reverse order. So the last thing that happened, or the last ability or spell that was cast, is the first thing that occurs in the Magic the Gathering stack. So then, these are not the only ways to traverse graphs. You can also have kind of like you can also like consider the cost of each of the edges, and then that is more of like Dijkstra's algorithm. You can consider the cost to get to the current node, and then also have like heuristic of like how far away you expect the the distance to the target node to be, and then that would be A star, which is kind of like an extension of a Dijkstra. The world of graph algorithms is vast and incountable, and I do not know everything about them. So, but anyway, so that is my brief talk on graph algorithms. I need to figure out a better setup, and also like just use Krita more. I hope this was interesting and educational. I hope you enjoyed. I'm going to make a video soon on how I used the flow field pathfinding for my tower defense game, and how I implemented it. So that'll be more practical. That'll have some code. That'll have also some very basic like beta gameplay to look at. It's probably alpha, whatever. Like some like pre-game ready gameplay that you can look at. So again, thanks for watching. Hope you enjoyed. Let me know if there's anything in particular that you'd like me to do a quasi lecture on in the comments. Like and subscribe if you like the video, and I will see you in the next one.